Okay. Hypothesis tests. These are going to look very, very, very similar to the confidence intervals. The process is going to be almost the same. It's just that now we're going to do a hypothesis test. So instead of giving an estimate for the slope, which is what the confidence interval is doing, giving lower and upper bound for the slope, instead we are doing a hypothesis test where our null hypothesis is that the slope is some value, and the alternative is that the slope is a different value. And usually, not always, but usually, the null hypothesis is going to be that our slope is 0. And the alternative is going to be that our slope is either not 0 or greater than 0 or less than 0. So, for example, if we wanted to know whether there was a positive association or a positive relationship between these two variables, a positive association, then our null would be that the slope is 0, and our alternative is that the slope is greater than 0. So we see whether we have a positive slope and therefore a positive relationship between two variables. So that is what our null and alternative usually end up being. N minus 2 degrees of freedom. It's going to be value minus the parameters. So our actual value for the slope minus what the null hypothesis says the slope is over the standard error. And again, the standard error is usually just told to you. You can just find it in the table. And then whether it's one-sided, two-sided, we'll tell you which way the tail is going to go for the p-value. So let's look at an example. Here's our example. So this time we're not going to deal with a whole bunch of calculator nonsense like we did the other day. Today we are using the table. So the key parts of the table, don't forget, is I will actually talk about this in just a second. Here's our slope, since it's attached to my x variable. And then here is my standard error for the slope. So that's going to go at the bottom of the formula for the t-score on the denominator. Is going to go the standard error. Oh, and look, this one asked, do the data provide convincing evidence that there's a positive linear relationship? So I just gave away what the null and alternative was on this one. Our null hypothesis is going to be that that beta is 0. So beta is our true slope of the regression line. So again, we're just using the Greek letter for b to keep track of our slope. So since we're trying to determine whether there's a positive association, we want the slope to be positive. So our null is going to be the slope is 0. Our alternative says the slope is greater than 0, so that it's positive. Alpha is 0.05. Here come our conditions. We're ready for the marathon. This is a linear regression t-test. Again, your calculator will basically outline that for you. Linear. No clear pattern in the residuals. Line seems like an okay fit. This is the normal probability plot over here. So we can that'll help with our normal condition as well. The other one I want to highlight again is equal variance. Residual plot shows a fairly equal amount of scatter around the horizontal line at 0 for all x values. So if I kind of trace out how spread out the data is, Aside from like this one point up here at like 50, most of the other data are about this far spread out, and it doesn't get too much wider or too much narrower in how spread out things are between those. And then our usual, normal, independent, and of course random. The 38 were randomly selected. Step 3. We are going to do our formula. Well, remember, our null hypothesis is that the slope is 0. So our value for the slope, minus our null hypothesis says that the slope is 0, divided by our standard error, that ends up being 3.07. And we want the right tail, since this is a one-sided test. And so that's going to end up being 0.002. And that's less than our alpha of 0.05. So we're going to reject the null hypothesis and conclude that there is a positive association. In other words, that the slope is positive. So rejecting a null hypothesis, we have enough evidence to conclude our alternative. Now, let me point out one more thing that you may have noticed them using arrows to point to. This, the t-score and p-value here that they show. This is the t-score and the p-value for the hypothesis test, the two-sided hypothesis test, beta equals 0 versus beta is not equal to 0. So that's what the values in that table are giving you. So it's giving you what the t-score is, and it's giving you the p-value for the two-sided test centered at 0. So just keep in mind, if our null and alternative or anything else or at anywhere else aside from 0, these values do nothing for you. They don't help you at all. But usually our null and alternative are going to be our slope is 0 versus our slope is not 0, or our slope is 0 versus our slope being greater than 0. In that case, this does help you. The reason it does help you is because since this is my two-sided test p-value, and I want to get to the one-sided test p-value, then we can just take my 0.004 and cut it in half, because I only want the right tail, to be 0.002. Now, you can also plug into the formula this way and do the TCDF that way, but also this table will give you some of that information. Again, that's only when we're centering our null hypothesis at the slope being 0 versus the slope being less than, greater than, or not equal to 0. Okay, and those are the hypothesis tests. Again, for the most part, a lot of these bits of information, you don't need to memorize some formula. A large part of it is, can you read the values off the table and find the pieces that you need? Now, if it does give you a list 1 and list 2, then you can put list 1 and list 2 into the calculator and go to linear regression t-test and have it do that for you. But a lot of the time, it'll have a table like this and ask you to be able to pinpoint and read the values off of it.